Welcome to our day on geometric probability. So geometric is often taught with binomial, but I wanted to separate them to make sure we understand the difference between the two. I think it's easy for them to become merged together in your mind if we do them at the same day. Okay, so bottle flipping. I don't know about you, but this drove me nuts when students would take their bottles. It always seemed to be freshmen that were doing this in my classes. That's back when I had Algebra 2. Okay, so this guy is going to flip his bottle, the water bottle, and he says he can land it right side up 20% of the time. And we assume that each time flipping is independent, that doing it one time will not impact the next time. So we're going to make that assumption. So if he flips the bottle 10 times, how many times do you expect it to land right side up? So let's go over this together. First, I want to decide, is this a binomial probability or not? So can I make that assumption? Well, binary, so success would be defined as landing on the right side up. Failure would be not landing right side up. Independence, we said we're assuming that. N, set number of trials, we want to see out of 10 times, so yep. And S, the probability, yep, the probability is 20% every time. So let's take a look here. The probability of landing right side up, the way we would expect the number of successes is going to be 10. So that's N times P equals 2. That's the expected number of successes. The probability that he makes exactly 2 flips. Again, to get exactly 2, not up to and including 2, but to get exactly 2, this is the 10 combination of 2. Probability of success raised to the number of successes we want, multiplied by the probability of failure times the number of failures. And again, the number of failures is the number of trials minus the number of successes. And we get 0.320. The probability that he makes less than 2 flips, so that would be 0 or 1. And again, we're going to do the same thing for these, calculate each of those, and we get that probability. The probability that he makes at most 2. So at most 2 is the same, and let me show you these, as making less than or equal to 2. So it's the probability of making 0 plus the probability of making 1 plus the probability of making 2. And we add those together and get 0.6778. Now, there is an easier way to do both of these, and we've done this before. Binomial PDF for just a point, an exact value. Remember, you would have to write down binomial PDF, parentheses, n is equal to 10, p is 0.2, and x is 2. You have to designate the variable letter as well as just the value. And here, less than or equal to 2 is binomial CDF. So again, 10 trials, probability is 0.2, and the number of successes is, because I'm using CDF, it's cumulative, up to and including 2 successes. Okay. That's this number 3. I could have used binomial CDF on this, but it would have been CDF of 10.2 and a 1, because the most successes you could have if you want less than 2 would be 1. Okay. He wants to do 10 more, but his teacher is getting annoyed. That sounds like it would have been me. And so instead of just saying he can do 10 more, we're going to say he can only go until he gets a success, till the bottle lands right side up. So this is what's making it geometric now, is that we're going to say he must stop once it lands right side up. Okay, the probability that he will land it on the first try is 0.2. All right, that's just a given. The probability that he fails on the first try but lands it on the second. So failure probability is 0.8. Probability of success is 0.2. And I multiply those together because I want them to happen in this order. I get a failure, then a success. So that's 0.16. Probability that he fails on the first 2 and lands it on the third try. Again, failure probability times failure times success. That gives me a 0.128. Probability that he fails the first 3 and lands it on the fourth try. So again, zero 0.8 times 0.8 times 0.8 times the probability of success gives me 0.124. And if we look at this is the same as 0.8 to the third power times 0.2 to the first power. So now if I say let x equal the number of flips it takes until he gets the right side up. So again, number of takes it takes for him to do this or until it lands a success. I can fill in this table. These first ones we've already done. For number 5, the formula I'm going to have to use here is going to be 0.8 to the fourth times 0.2. This one is going to be 0.0 or 0.8 raised to the fifth power times 0.2. What is the probability that he lands it on the 10th try? And this is assuming that he did not land it on the other. So the first time, this is the first success. So the first success is on the 10th try. Is 0.8 to the ninth power times 0.2 to the first power. And again, so I'm saying that if I want the success to be k number of trials, some people will use a little x here, but I think it's harder to tell them apart. So it's going to be the probability of failure to the k minus 1 times the probability of success to the first power. But this is our generic rule if we're dealing with geometric. And again, geometric is that we do not have a set number of trials. We are going to continue to do something until we get a success. So let's turn it over and sum these up and look at the check for understanding. Okay, so summing up these ideas, for a geometric setting, we use bits. So instead of an N, we have a T. It has to be a binary situation where there's success and failure. Those are the only two options. The trials have to be independent. We have to continue our trials until we have success. So it's not a set number. That's what's changing, is the number of trials. And S is the same probability. So everything is the exact same except for the T versus N. In a binomial situation, we have a set number of trials. In a geometric, we have a variable number of times it takes until you reach your success. If we are dealing with a geometric setting, our probability for success is going to be equal to 1 minus p. So my failure probability raised to the x minus 1. So if I want to see the probability that it takes 7 times, I'm going to have 7 minus 1 as my exponent. And I'm going to multiply that by p raised to the first power. So it's the probability of failure raised to the 1 less of what you want to achieve times the probability of success. And if we want to describe a geometric distribution, these are a couple new formulas for you. First of all, the shape is right skewed, and I did not show that to you on the other side. I'll flip back in a second. At the center, the mean, we find by 1 divided by the probability of success. So again, the mean is going to be 1 divided by probability of success. Remember, with a binomial, it was n times p gave us this. The measure for variability for a geometric distribution is going to be 1 minus p, so that's your probability of failure, divided by the probability of success, and square rooted. So let's take a look at these. Okay, the first one we're going to look at, read through the problem, and then I will cover these. So B, again, we do have, it's binary. Success is that Mason gets a pencil. Failure is he does not get a pencil from whoever he asks. I, each time is independent because you don't know, if one student doesn't have a pencil, that won't impact another student. T, Mason is going to ask until he finds someone to give him a pencil. So that makes it geometric, not binomial. And the same probability. The probability is 0.15 of getting a pencil at any one time. So what is the probability that the third person asked is the first one who gives him a pencil? So we want to find the probability of success on the third time. So the probability of success on the third time is going to be the probability of failure. So that's 1 minus 0.15 raised to the exponent of the number of successes we desire minus 1. So 3 minus 1 gives me a 2 times the probability of success. And notice on this, we always have the probability of success at the end, and it's always to the first power. And that gives you 0.1084. What is the probability that he gets a pencil by the third person? So this means I've got to look at the probability he gets it on the first person he asks, plus the probability he gets it on the second person he asks, and the probability of the third person. So I want to add those together. And there is another option on the calculator, geometric CDF. And again, the C stands for cumulative. I want everything up to and including that X value. So again, we labeled them. The probability of success is 0.15. X, the value of, or the number of success until we get a certain success would be 3 in this case. And how many people should he expect to ask? So what is the mean, basically? The mean is 1 divided by P. So 1 divided by 0.015 gives us 6.67. So he expects to have to ask 6.67 people before he gets a pencil. Okay. And then this next question, should he be surprised if he doesn't get a pencil until he asked at least 10 people? So we're looking for the probability that it takes 10 or more people for him to ask before he gets a pencil. So again, the calculator doesn't do stuff to the right on a distribution, it does to the left. So I'm going to have to look at what is the probability, the cumulative probability of getting less than 10 and subtract that from 1. So that's what I've written over here. So the probability of greater than or equal to 10 is equal to 1 minus the probability of X being less than or equal to 9. So I calculate that using the geometric CDF with a 0.15 for P and a 9 for X. And again, I'm using 9 because the value of 10 I want included. I don't want included, excuse me. So I calculate that and then subtract it from 1, I get 0.2316. And the question, though, is should he be surprised? No. Remember, our threshold for things being unlikely is 0.05 or 5%. We've got 0.2316. So it's not unlikely to happen that it takes up to 10 people before he gets a pencil. So he should not be surprised. That's perfectly normal. And finally, we want to calculate the standard deviation. And the standard deviation is the square root of the probability of failure, so 1 minus the probability of success, divided by, and this is not under the square root, 0.15, which is your probability of success. And it's 6.146. And if I had to interpret that, and I didn't write this down, because it's unusual for it not to ask for that, would say if he asked many, many, many people, did it many different times, and started the count over each time he got a pencil, the number of people he would have to ask for a pencil typically varies by 6.146 people from the mean of 6.67 people. Okay? And I said I'd come back to the histogram just to quickly show it to you. Here's what a geometric histogram looks like. It's skewed to the right. So this is a probability of doing something once, twice, 3 times. So the number of successes is on, number of times until success is on the x-axis. Okay, there is a homework online for you. It's titled Bolger's Geometric Probability, and it's also from section 6.3. Okay, have a good time. For A-Day students, have a great Thanksgiving. B-Day, I hope you had a great Thanksgiving.